Welcome back to AI, from zero to researcher. In episode 8, we built attention from scratch. Queries, keys, values, and the softmax weighting that lets a model decide what to focus on. Today, we take that mechanism and assemble the full architecture around it, the transformer. This is episode 9. If queries, keys, and values are not yet intuitive, go back to episode 8 first. Today, we stack and extend that mechanism rather than rederive it. In 2017, a paper called "Attention is All You Need" removed recurrence entirely and replaced it with stacked attention. It changed everything. Let's build the whole thing, block by block. Before transformers, attention was an add-on, something bolted onto RNNs to help with long-range dependencies. The 2017 insight was radical. What if attention is the only thing you need? No recurrence. No convolutions. Just attention, repeated and structured carefully. The result was faster to train, easier to scale, and better at capturing long-range patterns. Within 2 years, it became the default architecture for language. Within 5, it spread to vision, audio, biology, and robotics. Let's see why. A transformer is built from repeated blocks. Each block has the same internal structure. Let's build one. Step 1. Multi-head self-attention. The input sequence passes through the attention mechanism we built in episode 8. Every token attends to every other token, producing a new set of context-aware representations. Step 2. Residual connection and layer normalization. The attention output is added back to the original input. That's the residual connection. Then the result is normalized. This is critical. Without residual connections, gradients would struggle to flow through a stack of 12 or 24 or 96 blocks. We covered vanishing gradients in episode 4. Residuals are one of the main defenses. Think of it like photocopying a document before editing. The attention layer edits the representation, but the residual connection keeps the original copy. If the edit is unhelpful, the original information survives. Let's see this with real numbers. The input vector is shown on top, the attention output below. The residual connection adds them element-wise. You can see each pair of values combining. The result preserves the original signal, enriched by what attention found. Layer norm centers each vector to zero mean and scales it to unit variance. Watch the bars shift. The values center around 0 and normalize to a consistent range. This keeps activation stable, which is critical for training deep networks. The residual keeps the original signal alive. Layer norm keeps the values in a stable range. Together, they make deep stacking possible. Step 3. A position-wise feed-forward network. This is just 2 linear layers with a non-linearity in between, applied independently to each token position. Attention mixed information across positions. The feed-forward network now transforms each token's representation individually, adding non-linear capacity. Step 4. Another residual connection and layer normalization. That's one transformer block. Self-attention, add a norm, feed forward, add a norm. The entire architecture is just this block, repeated. N equals 6 in the original paper. N equals 12 in GPT-2. N equals 96 in GPT-3. Here's a key insight. The architecture separates 2 concerns. Attention handles communication, letting tokens share information across positions. The feed-forward network handles computation, transforming each token's representation. Communication, then computation, repeated. One practical consequence to plant now, self-attention computes a score for every pair of tokens. For a sequence of n tokens, That is an n-squared matrix. Double the sequence length, and the attention computation quadruples. A 10 by 10 attention matrix, 100 cells. Then, a 100 by 100 matrix, 10,000 cells. Then, a 1000 by 1000 matrix, 1 million cells. This quadratic cost is why early models had small context windows. The original transformer used 512 tokens. GPT-2 used IO224. For years, 4296 was considered the practical limit. Today, models like GPT-4 and Claude handle 128,000 tokens or more, but only through engineering breakthroughs like sparse attention, flash attention, and better hardware. The fundamental quadratic cost hasn't gone away, we've just gotten better at managing it. This is an active research area. Techniques like sparse attention only attend to nearby tokens, plus a few distant ones. Linear attention approximates the full matrix with lower cost. And sliding window approaches use a fixed local window. They all try to break the n-squared barrier. We will not cover them in detail here. But knowing that the quadratic cost exists tells you why context length is a headline feature of every new model. And why efficient attention is one of the most important open problems in the field. In episode 8, we computed one set of attention weights. But a single attention pattern can only capture one type of relationship at a time. What if the cat sat on the mat because it was tired requires one pattern for syntactic structure and a different pattern for coreference? Think of it like a committee of experts. Instead of one person trying to notice everything about a sentence, you have several specialists. One focuses on grammar, another on meaning, another on patterns. Each gives their perspective, and the model combines them all. Multi-head attention solves this. Instead of one attention computation, we run several in parallel, each called a head. Here's the math. We start with queries, keys, and values, all projected from the input. Instead of using one large projection, we split each into h smaller projections. If our model dimension is 512 and we use 8 heads, each head works with vectors of dimension 512 over 8, dk, equals 64. Let's make this concrete with a small example. Say dimension model is 8, and we use 2 heads, so each head works with 4 dimensions. Watch the vector split in half. The first 4 values go to head 1, the last 4 to head 2. Each head runs attention independently on its own slice. The same split happens to keys and values. For each head sub I equals attention of q times w sub I q, k times w sub I k, v times w sub I v. Each head has its own learned projection matrices. Each head computes its own attention weights. Each head can focus on different relationships. Let's walk through what one head actually computes. We take the query, key, and value slices for that head. We compute dot products between the query and all keys, just like episode 8. We scale by the square root of dk, apply softmax, and get a set of attention weights. Then we multiply those weights by the values to get the head's output. Now here is the key benefit. Because each head has its own projection matrices, each head learns to attend to different things. Look at these 4 heads. Head 1 focuses on adjacent words, local syntax. Head 2 connects it back to cat, coreference. Head 3 tracks punctuation. Head 4 is diffuse and hard to interpret. The model does not guarantee that every head has a clean, human-readable purpose. Some do, some don't. After all heads compute their outputs independently, we concatenate the results and project back to the original dimension. Multi-head of q, k, v equals concat of head 1 through head h times wo. The outputs from both heads are placed side by side, concatenated back to the original dimension. You can see head 1's values in one color and head 2's in another. The final projection through WO mixes information across heads. The total computation cost is similar to single-head attention with the full dimension. We just split the work into parallel, specialized streams. One caveat from episode 8's research habit: be cautious about interpreting what individual heads do. Some heads learn clean, interpretable patterns. Others don't. The model doesn't promise that each head has a human-readable purpose. There's a problem we haven't addressed. Self-attention treats the input as a set, not a sequence. It computes pairwise interactions between all positions, but it has no idea which token comes first. Dog bites man and man bites dog would produce the same attention weights if the embeddings were simply looked up by word identity. Without position, attention treats words like people in a crowd. It knows who is there but not where anyone stands. Positional encoding is like assigning seat numbers. Now the model knows that word 3 sits between word 2 and word 4. We need to inject position information. Each position gets a unique signature, a pattern of values that the model uses to know where each token sits. This is what positional encoding looks like. Each row is a position. Each column is a dimension. Notice the wave patterns. Low frequency waves on the left, high frequency on the right. The pattern comes from alternating sine and cosine functions at different frequencies. The formula takes two inputs. Pos is the position of the token in the sequence. First word is 0, second is 1, and so on. And I is the dimension index, which slot in the encoding vector we are filling. For even dimensions, we use sine. For odd dimensions, we use cosine. The denominator creates a different frequency for each dimension. Low dimensions oscillate fast, high dimensions oscillate slowly. The constant 1000 just controls the range of frequencies, and D model is the size of the embedding vector. Let's compute a few values to see the pattern. For position 0, the formula gives us 0 and 1 for the first two dimensions. You can see them appearing in the first row. For position 1, we get 0.84 and 0.54, already very different. Each position produces a unique fingerprint of values. The math is just sine and cosine evaluated at different frequencies. Follow the formula on screen if you like, but the key idea is every position gets a distinct signature. Now, look at position 2 in the table. The values shift again, 0.91 and negative 0.42. Every position is distinct from every other. But here is the crucial insight about dimensions. The low-numbered dimensions change rapidly between positions. The high-numbered dimensions change slowly. They barely shift from one position to the next. This mix of fast and slow frequencies is deliberate. The fast dimensions help distinguish nearby positions. The slow dimensions help distinguish far apart positions, giving the model both fine-grained and coarse position signals. Why sine and cosine? Because for any fixed offset k, the encoding at position pos plus k can be written as a linear combination of the encoding at position pos. This means the model can learn to compute relative positions. This token is 3 positions before that one, using simple linear operations within the attention mechanism. These encodings are added directly to the input embeddings before attention. The model then learned to use both content and position when computing attention weights. Other approaches exist. Learned positional embeddings let the model discover its own position representations. This is what GPT-2 and BERT used. Rotary positional embeddings, ROPE, encode relative position directly into the attention computation and have become common in recent models. The core principle is the same. Attention alone is position blind, so position must be supplied as an input signal. The transformer block is a building block. how you arrange it, and what you let it see creates different architectures for different purposes. Encoder-only models process the full input with bidirectional attention. Every token can attend to every other token, including future ones. This is ideal for understanding tasks, classification, named entity recognition, semantic similarity. BERT is the most famous example. Decoder-only models use masked self-attention. Each token can only attend to itself and the tokens that came before it, never the future. This is the autoregressive setup. The model generates one token at a time, left to right. GPT and most large language models use this design. That mask is just a matrix of allowed and blocked attention connections. During training, it lets the model process the entire sequence in parallel while still ensuring that predictions at position T only depend on positions 1 through T. Encoder-decoder models combine both. The encoder processes the input bidirectionally. The decoder generates output autoregressively, but also cross-attends to the encoder's representations. This was the original transformer design, built for machine translation. T5 is a well-known modern example. Here's this episode's research habit: separate architecture from training objective when analyzing model behavior. The same encoder-only architecture trained with masked language modeling gives you BERT. Trained with a different objective, it would learn different things. Architecture defines what computations are possible. The objective defines what the model is pushed to learn. This distinction matters most for pre-training, the large-scale initial training phase that gives transformers their general capabilities. The model predicts CAT with 87% confidence. Causal language modeling, CLM, predict the next token given all previous tokens. The model only sees the past, never the future. This is how GPT-style models learn. Both objectives are forms of self-supervised learning. The labels come from the text itself, not from human annotation. This is what makes it possible to train on billions of documents without labeling any of them. Notice the link back to episode 4. The architecture tells us what computations are possible. The objective tells us what gradients flow through the model. A decoder-only transformer trained with next token prediction learns to generate. An encoder-only transformer trained with masked prediction learns to understand context. Same building block. Different objectives. Different capabilities. Let's build a single transformer block in PyTorch and feed a sentence through it. We'll use PyTorch's built-in modules so the code stays focused on the architecture. Now let's feed a sentence through it. The input and output have identical shapes, batch size, sequence length, model dimension. That's what makes stacking possible. The output of one block feeds directly into the next. The attention weights are a 7 by 7 matrix, each token's attention to every other token. Note, we use module list, not sequential, because each block returns a tuple of output and attention weights, and we need to handle that explicitly. This is a common pattern in real transformer code. This is the building block. Stack 12 of these, and you have a small language model. The shape never changes. Each block refines the representations, mixing information across positions through attention and transforming each position through the feed-forward network. After 12 blocks, each token's representation is a rich, context-dependent vector that encodes information from the entire sequence. Output difference without positional encoding. Essentially 0. Output difference with positional encoding to 195. Without positional encoding, the difference is exactly 0. The cat sat on the mat, and, on mat, cat. The sat the. produce identical outputs up to reordering. The transformer literally cannot distinguish word order. It treats the input as a bag of tokens. With positional encoding, the outputs differ. The model now knows that cat in position 2 is different from cat in position 5. Order matters. This is why positional encoding is not optional. It is the only source of sequence information in the entire architecture. Remove it, and the transformer loses the ability to understand that dog bites man and man bites dog mean different things. Let's compress what we covered. A transformer block has 4 components: multi-head self-attention, residual connection with layer norm, a feed-forward network, and another residual connection with layer norm. Attention handles communication between positions. The feed-forward network handles computation at each position. Multi-head attention splits queries, keys, and values into parallel heads, runs attention independently in each head, and concatenates the results. This lets the model capture multiple types of relationships simultaneously. Positional encoding injects sequence order into an otherwise position-blind architecture. Options include sinusoidal, learned, and rotary encodings. 3 major variants exist: encoder, only for understanding; decoder, only for generation; and encoder-decoder for sequence-to-sequence tasks. The same building block serves all 3. The difference is in the attention mask and the training objective. And the research habit: always separate architecture from training objective. The architecture defines what is computable. The objective defines what is learned. We've built the transformer from its parts. But knowing the architecture is only half the story. In episode 10, we ask a deeper question. What happens when you train a decoder-only transformer to predict the next token billions of times on the entire internet? The answer turns out to be more interesting and more complicated than anyone expected. We'll look at what language models actually learn during pre-training, why they can do things they were never explicitly trained to do, and how fine-tuning, instruction tuning, and reinforcement learning from human feedback turn a raw text predictor into something you can have a conversation with. Here's a question to carry forward. If the transformer is just a stack of attention and feed-forward layers, and the training objective is just predict the next word, where does the apparent intelligence come from? Is it in the architecture, the data, the scale, or something about the interaction of all 3? That's episode 10.